in terms of lines of code, up to 71% of the code base of an application is belonging to open source components embedded therein. And if we speak in terms of the number of components, again, there are studies showing that this is up to 86% of the components that are actually open source components ending up in an application. And so this obviously depends a little bit and changes from one ecosystem to another ecosystem. But what remains important here is that a great share of today's applications is from open source projects. And the other important takeaway is vulnerable dependencies, no matter where they are in a dependency tree or graph, those vulnerable dependencies can impact the security of the application, just like any vulnerable first-party code, right? It doesn't matter whether this is a direct or transitive dependency. It can impact the confidentiality, integrity, or availability of the application. So we have this aspect on the one hand, and the other aspect is the increasing number of advisories being disclosed in the public. So what you see on the right-hand side in the bottom is a bar chart that I just created a few days back on NVD, and it's showing this constant increase of CVEs being published over the course of the years. So on the right-hand side, the orange bar is the number of vulnerabilities disclosed in 2024. And you see, even though we're not even at the end of August, we already have as many CVEs as we had 2022. And we're almost certainly extending or going beyond the number of vulnerabilities of the last year. Again, like for the 7th or 8th year in a row. I think this is due to increased awareness. What is important also to remember is that not all open source vulnerabilities end up getting a CVE. This is especially true for the NPM ecosystem. And both of these facts basically contribute to have a very kind of devastating impact in the sense that software composition analysis tools basically overwhelm developers with findings in the many open source dependencies they have with all those vulnerabilities. And this is causing major efforts and can lead to alert fatigue in case those findings turn out to be not relevant in a given application scope. So why does it cause efforts? Well, what you see on this slide are typical activities part of, let's say, vulnerability management or risk management. And so those activities need to be done for all the vulnerabilities reported for your application or the open source components contained therein. The first thing is you need to understand whether a vulnerability is really exploitable in the context of your specific application and what would be the impact. So what comes into play here is kind of what does your application do in the first place, right? Is it an application to manage and to show the menu of a company's canteen, opposed to does it deal with PII or other sensitive information, credit card information, and so forth. So there's this aspect coming into the assessment and management, but also whether the vulnerable code can actually be exploited. I will come to this a little bit more in detail on the next slide. The other activity is to kind of understand the likelihood of a vulnerability being exploited by attackers, which is going hand in hand with the ease of an attack. And so here you need to answer questions like, are there any ready-made exploits available that can be just downloaded from the internet and be used easily by attackers? Or does it really require, a sophisticated attack that is requiring significant resources? Or have there any attacks been observed already in the past? And the last bit playing into vulnerability management and this whole decision-making process is, well, how can I fix this vulnerability? Are there OSS fixes available provided by the open source project? If yes, do they introduce any breaking changes that impact the behavior of my application? What is the effort to implement an update or implement even a custom fix, and so forth. So these are 3 activities that require being done for those vulnerabilities, and all of them come with a significant or kind of some effort, let's say. Going a little bit more into details into this exploitability assessment. So this answering the question whether a vulnerability in any of your dependencies is exploitable in a specific application running somewhere on some system requires a lot of context information that is hardly available or hardly described in some systematic machine readable form. And so this is information, context information, such as what's the attack surface of the application? So what are all the different kind of interaction points at the disposal of attackers to input data to the application, to extract data from the application or otherwise interact with it, right? So is this, for example, an application which is available and accessible anonymously to all the people in the internet, or is this maybe an application that is only, which is not externally facing, only used by a few people within a company? Other context information is whether there are any mitigating controls already in place, like web application firewalls, or maybe the developers of the application kind of saw problems coming and implemented their own sanitization method already for input sanitization or so. And yet another aspect to be taken into account is some vulnerabilities only become relevant in case certain configurations are in place, like certain, command line options being activated for the runtime environment, or certain configuration settings being put, or for certain versions of, let's say, Java runtime environments. And so all of that is hardly automatable, which is why we think a very good, let's say, approach to answer this exploitability question is to look at the reachability of vulnerable code, which we call reachability analysis, which means that we try to establish whether a vulnerable function somewhere in your open source components can be executed if you run your application. And this decision is made on the basis of the code of the application and the open source components, which is readily available in the development environment. So we can automate this much better. And this is helping us because reachability is the prerequisite for exploitability, right? If a vulnerable function cannot be in no way executed as part of an application, it can also not be exploited. And so here this whole reachability analysis takes advantage of the fact that a large share of the open source dependencies that are part of your application is in fact not used. So there are certain features of open source components that are not really required in the application. And reachability is trying to, sort this out. Is this code of an open source component used or not? And again, internal studies show that up to 88% of the lines of code of projects or applications is not really used downstream. So this number, as well as the numbers 2 slides back, they come from our State of Dependency Management Report 2023. I've linked it here, but you can also find it in our resources on our webpage. All right, one step back. Remember those 3 activities I've mentioned: exploitability, probability or likeliness, as well as remediation. So all those aspects, they contribute and help developers to focus on those vulnerabilities that matter most and which can be fixed, right? And what you see on the right-hand side is kind of a bar chart for the Maven ecosystem computed over the tenants in our production system that show that applying different filters can reduce the number of vulnerabilities to let you focus on exactly those things. Those that where a fix is available, where the probability of an exploit is greater than 1% in this example, or where there are reachable functions. And we see that if we combine all those filters together, in this particular case here for the Maven ecosystem, only around about 4% or so of the vulnerabilities fulfill all this criteria. And so these are the ones that you would address and attack first when it comes to managing open source vulnerabilities. All right, and that basically concludes my introductory part. I would like to hand over to David for basically showing how this whole prioritization works in our platform. Please.
Thank you, Henrik. Just share my screen, give that a second to load. So yeah, I'm going to give you a quick demo to show you how some of this theory can be put into practice. And also just highlight that with a very relatively small number of projects, you can end up with quite a considerable vulnerability backlog with scary numbers. So this is something that I see commonly. I work in the solution architecture team at Endor Labs, so we often look at customer projects, and it's not uncommon for us to see 10, 20,000 vulnerabilities within this prioritization funnel. So as Henrik's kind of alluded to, there's a lot of missing data when it comes to prioritization of vulnerabilities. And typically what I see customers doing is trying to prioritize just for impact. So if we take the CVSS score as a proxy for impact here, and I just maybe filter out highs and lows, we still have quite a considerable number of open vulnerabilities in the backlog. And this is why people are struggling to prioritize what they have based on the data of impact alone. So the relative sort of value that we can add here is understanding the context of use. So the first thing that we can do is filter out those vulnerabilities that are in test dependencies, right? Because those things don't generally go into production environments. So we can ask developers to focus on vulnerabilities in dependencies that go into production environments. We also want the developers to focus on where there's a fix available. If you don't have a fix available for a library, then it's quite difficult for a developer to resolve. They'll end up researching that vulnerability for a long period of time and forking the dependency, etc. So we try to encourage people to prioritize on the backlog where they have a fix available first. And then comes reachability. So as Henrik described, we are able to analyze your first-party code, understand how you use your direct dependencies, and then we understand how those direct dependencies interact with transient dependencies that appear further down the chain. This gives us a reachability factor. So we understand that there's a call path between your own source code and the packages in your repo to the actual dependencies that you use. But that doesn't tell us anything about likelihood, right? A lot of vulnerabilities are maybe theoretical in nature, or they don't have, for instance, POCs available, they're not included in exploit kits, etc. So we add in an additional level of context, which is the EPSS score. You can configure this how you wish to, but EPSS tells us the likelihood of exploit within the next 30 days for a vulnerability. This is based on an ML model. There are many different feeds that are included within this number, and this number can go up and down for any particular CV on any day. So it's important to monitor this, but it tells us that we have a greater than 3% chance of exploit for these 88 reachable vulnerabilities in the environment. So immediately we go from a figure that's very unwieldy and difficult to work with to something that's very actionable, that we can help the developers prioritize those vulnerabilities. So I'm just going to click through here and have a look at some of this in detail. So immediately from clicking through, I already have filtered for the things that we want to remove here. So I know these CVs have fixes available. I know the function's reachable. I know that they're not in test dependencies. I also know that we have an EPSS score set, and we're just looking at the vulnerability categorization. And what I end up with is the list of 88. And for any given vulnerability here, we can quickly open the tray and understand exactly where it lies. So what we're viewing here is that we have a repo. It's this repo here. We have a number of packages in the repo, but the vulnerability is in the shop easy package, which is a Java package. And then finally, the vulnerability itself lies in this dependency, which is commons file upload. The risk details are here, along with additional notes and so on. This is basically a denial of service vulnerability through a malicious content type header, so probably not super difficult to exploit. We understand which versions it applies to and so on. We understand the dependency path, but perhaps most importantly is the call paths. So this is where we understand exactly why this is reachable from the first-party code in the repo. So again, this is the repo that we're looking at. This is the package within the repo. Repos may have a number of packages within them for maybe back-end or front-end components or a number of different microservices, for example. This is the last line of first-party code, really, that we're seeing in the call path. That end up invoking a part of Spring Web, which invoked a part of Spring Core. And then we follow this call path all the way through to a function really where the CV exists within the library. So does this mean that this CV is exploitable? Well, absolutely not. Like Henrik explained, there could be other mitigating factors in place. There could be some environment factors, on the JVM version and things like that. But fundamentally, you should be able to understand that if something's not reachable, then it's not exploitable. And that's what we're trying to help developers with. Understand which ones are reachable, which ones they need to focus on, that they can get some remediation advice on. So moving into remediation advice, obviously we know the fixed version in here, but there's another benefit of having call path analysis within the product. If we understand how you use your first-party dependencies, and we understand how those dependencies use their own dependencies as well, we can start to make an idea about and predict how difficult an upgrade is for a library. So if I come into this info here and view full recommendation, at the moment we're just viewing a recommendation for the file upload library. What it will show is for each version upgrade, whether this is a medium level remediation risk, a low level remediation risk, or a high level remediation risk, and which findings are fixed from moving from one version to another. And we'll generally make a recommendation on what to move to. These ones happen to be a medium level remediation risk. So if I just pop the tray out here, what you'll see is that we have some potential conflicts within the transient dependencies. And the way that the JVM works is that you could end up loading like one version of a library, and then that's the version you load, and then you can break another part of your application that depends on a different version of the library. So we surface potential conflicts in here. And if I just clear the filters out here as well, see if we have some examples of maybe something that's a more difficult upgrade. Yeah, this is a good one, Hibernate Core. So if we go from the version that we're on, 4.0.1 final, to 4.1.1 final, it's a low remediation risk, right? That means that there shouldn't be any breaking changes, there's no dependency clashes, etc. If we try to move from this version to the 5.0.0 final version, I can see this is a high. And then if I open this out, and we can see some of the breaking changes within the source code. Now, statistically, this is how traditional tools try to do this. Sometimes they give upgrade advice, and it's based on statistics, which means that for all the people that tried to upgrade this library, how many did it successfully? Endor's working differently. It's looking at your source code, figuring out how you use those libraries, what APIs you use within those libraries, and making a recommendation based on that. So this is your risk, not like a sort of average across the industry. So at this point, if we have any sort of developers on the call, you're probably yelling at me that you don't want to come into yet another IDE. We help developers do the prioritization through policies, right? So we already have looked at the vulnerabilities that we care about. We meet developers in policies, and there's a number of policies available, but the key ones are finding policies. These are the things that we detect within an environment, including vulnerabilities. And then action policies dictate how we get these to developers. And actually, developers can consume results in a number of methods, all the way from the IDE through a CLI, through the pull request, which is generally most popular, giving feedback to developers in the pull request. CI/CD pipeline is another option. We can meet developers all the way through, depending on how they work. And setting up policies is quite straightforward. I'll give you an example for vulnerabilities, for example, because that's what we're looking at. If we were to set up a vulnerability policy, we could specify that we care about high or critical findings, where there is a fix available, where the function is reachable from the source code. We don't want to include test dependencies. And then we would basically, any finding that matched this, we can either break the build, so in CI, or block the pull request from happening, or we can warn if that's preferred. Or you can add it to a developer's backlog. So if it's something like an unmaintained library, you might choose to add it to the backlog, whereas it's something that you're introducing net new risk to your project, you probably want to deal with that, in the traditional workflows that the developer has when they're committing code. So hopefully that's a useful quick overview. I'm going to hand over to my colleague Joseph now, who's going to take us more into the science of program analysis, how it works, and talk about some of the benefits that I've described as well. Joseph, I think you're muted if you're speaking. no doubt some permissions issues with the platform here, so we'll just give Joseph a minute to rejoin.
Yeah, I think now I'm back again. Sorry for the technical problem. All right, so now we're gonna dig into a little bit what is the technology behind the reachability analysis. And before I start explaining how call graphs work and what they do behind the scenes, it's always good to start with how is a lot of the current day analysis working. And I think for a lot of us, we're very familiar with the package and build manifest. So normally, whether you're in Java with pop-XMLs or Gradle build files, or in JavaScript with npm files or Rust in Cargo, we normally would have, let's say, like the package manifest along with a couple of dependencies, right? And these are the direct dependencies that we have full control over, and we can edit them directly whenever we want to change or add a dependency. And normally the unit for analysis when it comes to finding out, for example, do you have a vulnerability or using any packages with vulnerable versions, is to essentially build a dependency tree, right? And normally you will find, for example, that there might be one version that has like a vulnerable version, or there's like some known performance bugs or other issues or outdated packages. And this is a little bit what Henrik and Dade was touching upon earlier, right? And then to find out is similar to the reachability analysis that we're explaining. You would, of course, apply some filtering criteria, and you will know exactly where in the dependency trees these vulnerabilities are. But then the problem is, like, as Henrik showed earlier, that the growing number of CVs is getting higher and higher by years, and it becomes very difficult to filter this out in general. And yeah, a little bit what I was touching on, like you have like this alert fatigue, but then what is the main problematic part is that we are not really judging or basing anything based on source code. We are simply just looking at package build manifest, and we know that when it comes to using third-party libraries, we don't use the entire library. We don't use the entire API service. We use a couple of methods, and how we use those methods really influence which or what parts of the source code is reachable, not reachable. And that's a kind of important point that sort of led us towards this whole part with doing analysis on the source code, is that we don't see manifest in general as being, like the usage of how we use dependencies. They're just purely declaration or a way for us to decide which dependencies we would like to import in our application. And moving in more to this whole part that we're using called static analysis or call graphs. So what we are essentially doing is that we have our dependency tree. Here, let's say like we have the application along with the different dependencies. So what we do here now is that we start going into source code, and the way to represent the source code is that we essentially take all the different functions that exist in your source code along with the dependencies, and then we start building a graph seeing how all those different components are used. So traditionally with static analysis, you would normally build call graphs as a way to build, let's say, like other more complicated analysis in general. But the way we use call graphs is to essentially approximate what kind of parts of the code are you using. So you can see, for example, here that we are, like having our main method, and this essentially calls other methods in the dependencies like validate XML, serialize, etc. And then another interesting part is that even though like you may import direct dependencies, you could also directly in your application import functionality from transitive dependencies. So if you see the example with the compress, this is something that let's say like the serialize method is using transitively, like here. And this is also something that you cannot directly see if you, for instance, use metadata analysis. So everything that is imported in your application is also available in your application. That includes transitive dependencies. And then comes, let's say, like the more interesting part. So how do we essentially enable or fine-grained prioritization? Well, by building this graphs of functions and how they connect to each other, be able to quickly see which parts are being used and not used, right? So if you look, for example, into the vulnerable function compress, we can directly see that there is a path to it from main to here. On the other hand, if you look into the bug that we discovered, or like a problematic function, we see that we are not really calling parse.json, right? Parse.json is essentially being called to escape character, but there's no path from main to here. And this is the way how we're able to filter out whether you're using some type of functionality or not in the source code. And this drastically impacts, let's say, like which functionality is being used or not used in the source code. So here we can say the result is that one of two, let's say, like problems or findings that we identified are potentially problematic for our application. And going further, because there's also like other types of reachability analysis, for example, that works on the AST level, where you essentially like, look into your source code, you see what kind of functions are being called to your direct dependency, but it, let's say, like doesn't go further than that. But we are kind of, something that we highlight very importantly is that it's very important to do inter-procedure analysis across the whole dependency tree and not only to direct dependencies. And the reason why this is important is that, for example, if you would normally look at this application, you would first count that, okay, the application app is essentially using 3 dependencies, like lib1, lib2, and then lib3. But in reality, if we follow along the code paths or execution paths, we can see that main is calling foo is calling bar, and bar is calling another bar in lib2. But here we see that this internal function is calling use in lib3, and we can see that lib3 is actually not used at all. It's only calling that. It's only calling that transitive dependency, but the way we're using lib1, we're not really calling to that function in lib2. So in practice, app is only using 2 dependencies and not 3 dependencies. And this is, let's say, like why it's very important to do this full-scale analysis on the dependency tree. And one very interesting thing on how we're doing it, since applications can easily scale up to 200 or even 300 dependencies. We even have cases with 400 dependencies. So trying to build that using the application together with all the dependencies will take many hours to do. But the way we do it is that we apply something that we call stitching, which is that we have essentially doing partial analysis of all the different dependencies that exist, open source, and similarly for internally in the organization, we build partial call graphs of those. And then when it comes to analysis time, we essentially combine all those call graphs and stitch them together so that we get a full representation. And we can do that in a couple of minutes. And this enables us to run all these different types of reachability analysis and such things. And finally, as a little bit highlighted, was that it does help enable us for when it comes to transitive dependencies. But there's also another type of category called phantom dependencies. And these are dependencies that are not visible in your build or dependency manifest, because you could, in the source code, immediately call, for example, pip install scipy with your code. And this is not declared in your requirements.txt, for example, or in your dependency build manifest. And by doing source code analysis, we're able to directly capture those dependencies, which means we also cover those, which are very important when it comes to building SBOMs. And another thing that Dave was touching upon before I took over was on upgrade impact analysis. Here, instead of using tests, which are quite common for regression analysis, we are also looking at, let's say, one problem with tests in general is that you may not write specific tests for dependencies. One common one is, for example, log4j, and most of us know a little bit about the log4shell incident rights. It's very unlikely that we have tests to, or even effective tests to essentially capture those changes that may happen in those libraries, right? So by having core graphs, we are able to, without any extra effort, getting this extra cover that we don't get from tests, right? To be able to test for changes in libraries and be able to quickly detect whether there are breaking changes or other forms of changes that may happen. And that's a great use case, like with static analysis here. And yeah, this is the end of our presentation. So now we leave the floor for any questions in the chat. And yeah, feel free to ask any questions that you have. Yeah.
Yeah, there was one in the question. Maybe we can try to. I started with an answer already, but I'm not sure it's covering everything. So one participant asked how our reachability analysis performs across different languages, compiled, high level, etc. And so my preliminary answer was not so much about the performance, but more the language support that we have, which is like 8 languages today, with additional ones being added. Yeah, but maybe I'm not sure who's going to take this. How do we approach this for different types of languages, interpreted ones, compiled ones, and so forth?
Yes, maybe I can take that one. So I think with every languages, there are always some different challenges. Some languages may have more dynamic feature, which makes it very difficult for core graph analysis. And other more static languages, there's maybe less problems in general. But I think the general approach that we have for any type of language that we address is that we try to focus on achieving as much soundness as possible, meaning that we aim to try not to be, let's say, like, missing potential paths, but we try to essentially, even if it means over approximating a bit, that's sort of like the choice that we generally have. And I think when it comes to languages, when it comes to building core graph, we essentially go for the medium where we have, let's say, like the most type information in general, or where it's a bit more easy. For example, in Java, we rely on the bytecode. In Python, we analyze the source code. So yeah, I mean, we don't think so much around that, but in general, our approach is to focus more on, covering as many language features as possible. Even though that might imply that we over approximate in some cases. I hope that answers the question.
I hope so too. There's another one asking whether we need to integrate with Git for source code to be available for analysis. And I think I can take this one. To my knowledge, this is not required. We can also scan just local directories or even certain archives.
Yeah, that's correct, Henrik. Yeah, we support scanning of jar files, for example, or Python wheels. So we can look at applications in their sort of compiled form as well.
Yeah, so there are basically 2 opportunities or 2 possibilities, right? You have we distribute a binary, and you can run this locally or in your CI/CD environment, and it would scan then whatever is on disk, or you install a GitHub application.
Yeah, those are the 2 most frequently used options for scanning. GitHub has the advantage of being able to, switch it on for all of your repos in one go. So there's obviously some benefits there for deployment. The alternative is to use Endor CTL, which is our single binary that we use for everything, and implement that within, like a CI/CD process, for example.
Right, thanks. And then we have another one. Does this application support Flutter code scan? I must admit, I don't know what the Flutter code scan is or could be, so I have troubles taking this one.
Yeah, Flutter is for mobile application development, I think. So yeah, it isn't something we support today. We do support Kotlin for Android applications, and basically iOS applications as well use CocoaPods. But yeah, unfortunately, we don't support Flutter yet.
All right, thanks. And we have another one asking how EPSS, so the exploit prediction, the exploit probability scoring system, how that differs from the traditional severity ratings like CVSS. I think this is what David already mentioned earlier on, right? So those EPSS scores are recomputed on a daily basis, right? Taking into account the latest information on ongoing attacks, campaigns, and also taking into consideration updated vulnerability information. While CVSS typically is more, let's say, statically describing the kind of impact or the characteristics of the vulnerability. Traditionally, there were also kind of temporal score available for CVSS, but to my knowledge, this has never been really taken off and being adopted in large scale.
Henrik, I do have a follow-up question to that. And do you feel, or do you have an opinion on whether CVSS is somewhat subjective and therefore not the best sole, usage for prioritization?
Yeah, I mean, if ever you did a CVSS rating yourself, some of the choices may be subjective. Do you consider the impact on the confidentiality high or medium or low? I think there are some definitions, but they still give room to a subjective kind of assessment of the situation. And if one chooses medium, the other chooses high, this can make a difference in the CVSS and the resulting CVSS score. So yeah. All right, I don't see any other questions coming in. So maybe we leave it with that, right? So I think we can maybe conclude the webinar. Thank you all for your attendance and the questions. Hope you liked it. You can, it will be shortly available on our website, and we wish you a nice day wherever you are.
Thanks for joining.